we're good.
All right. Well, thank you everybody for showing up here. My name is Justin. I am a staff engineer at a company called Firework. I hope that you all meant to come to this talk because, like Michael said, I was sort of a last-minute addition. It seems to be a going trend for me. I gave this talk at ElixirConf back in September, and I was given a week notice to actually write this talk and present it. So hopefully everybody gets a little something out of this. And yeah, let's go. So I assume most people use Postgres or some SQL dialect anyways in their day-to-day work. So hopefully they can, or sorry, hopefully this can sort of give you some idea of what you can do to sort of help yourself. So before we get started here, I'm going to do a little bit of terminology. Postgres has these concepts called a heap and a page. The heap, despite its name, is not a memory allocation heap like you would find in C. This is just the main storage area used by Postgres. And a page, or sometimes known as a block, is the smallest unit of storage that is used within Postgres. So with that out of the way, let's create a little tiny application. We're going to have 3 tables here. We're going to have a users table with a first and last name, a businesses table with a legal name, and just a table, a businesses users table that will join the 2 together. In our system, we're going to have 3 different queries, where the first one here is going to grab a user based off of an ID. The second one is going to grab a business based off of, or sorry, yeah, give you all businesses that are associated with a given user. And the third one is going to give you the reverse of that, all of the users given a specific business. It's worth pointing out, I think, that this is an approximate estimate, or this is an approximation of what you'll get if you do a preload within Ecto. It's not exact, but it's close enough, I think, for our purposes. So I'm going to make this a little bit interactive here. Is anybody familiar with what we can do to actually find performance issues at all within Postgres? Does anybody sort of do this in their day-to-day work today? Just feel free to shout out. Don't.
Explain.
Are you referring to explain?
Explain's a pretty good start, yeah. But the problem with explain is that you need to know a specific query in your system in order to actually utilize that. So what I like to do first is I like to try to use this thing called PG stat statements. This is my go-to extension within Postgres in order to start finding performance issues. Has anybody actually used PG stat statements before?
I do.
Perfect. A couple, or at least one person anyways. So just to quote the documentation here, PG stat statements module provides a means for tracking planning and execution statistics of all SQL statements executed by the server. That sounds kind of cool, but what does that actually mean? So let's take a quick look at what, or a query that I like to use in order to actually track this. Like all extensions within Postgres, you're going to need to actually do a create extension command. After that, you're going to have access to PG stat statements. It's going to start gathering in the background information about all of the queries that are actually run within your system. So in the case of the query here, this is going to return the first column is the parameterized query. What this means is that if you have that first query, select user where ID is equal to X, that X is going to be exactly that. It's an X, it's a variable. So all invocations of that are going to be counted as the exact same query. The second column is going to be the number of times that this query has been called within the system. The third one is going to be the amount of time in the mean execution time across. Sorry, I said that wrong. The second one is the total execution time across all invocations of that query. The third one is going to be the number of times it's called. The fourth is going to be the mean execution time of that query. And lastly, we have the time as a percentage of all queries that are run within the system. So let's take a quick look and see what that looks like. So in this case, it's kind of hard to see what it looks like just because, or sorry, the query there, just because I had to use a substring just to make it fit all in one slide. But you're going to have the query there, the total time, the number of times it's been called, the mean execution time, and the percentage overall. With this output, can anybody maybe suggest which query or queries we might want to look at?
I think the second one.
The second one is a good place to start. Yeah, the second and third one are going to be the queries that we're actually going to be looking at. Intuitively, we may want to look at the the top query, just because that one clearly takes the most amount of time. But if we look at the mean column, it is only 0.01 milliseconds. That's already super fast. I don't think we can probably do much to optimize that query. So in our case, we are going to look at the second query specifically, but this is going to apply to the third query as well. So as a couple of people mentioned already, we've got this thing called explain. So explain by itself is going to give us some estimates on what Postgres is actually going to do with a given query. We are going to also use the analyze option, which is going to give us some runtime characteristics. So explain by itself will not actually run the query. It's just going to give you those estimates. If you also tack on analyze, it will run the query and give you the not give you the normal result set, but tell you the runtime characteristics of what happened within the system. It is worth noting that there's a few other options that we can pass to explain to give you additional information, but we are just going to focus on the default output for explain and analyze today. So let's take a quick look at that query. If anybody's never used explain before, you literally just prepend your query with explain, and in our case, explain analyze, and Postgres is then going to spit out what's known as a query plan. So in this case, if we look down at the very bottom here, our execution time was actually rounded up to 1600 milliseconds. That is higher than the initial 830 milliseconds that we had. But remember that that is just a mean execution time. That is not guaranteed for every single invocation of that query. So what probably happened here is we probably had some sort of a cache miss. Something wasn't in memory, just something made it take longer. So if you've never looked at a query plan before, this can be probably quite daunting. There's a lot of information here. So let's try to sort of break that up a little bit. So we're going to start towards the bottom of the query, and we've got this thing called an index scan. This index scan is working off of the business's P key index. These P key indexes are created by Postgres automatically for any table that has a primary key in it. If you can see towards, can you see my pointer? I'm not sure. I don't usually use Zoom. Yeah?
Yeah.
Okay. You can see that this part of the query was never actually executed, so Postgres is not going to give us runtime characteristics about it. So what happens here is the first set of brackets here are the estimates that you would get if you only ran explain, and the second pair of brackets here, which we'll see more of later, is what actually happened with that query. So this cost thing is just a random arbitrary CPU unit type thing that Postgres uses. I don't fully understand the calculation. And then Postgres expects that we're going to return a single row with a width of 26 bytes, I believe it is. But the important part again is that in this particular case, we never actually executed something. The index scan is actually one of the faster pieces or sort of like faster query metrics that you can get. It's only beaten, generally speaking, by an index only scan, which I'll get to a little bit later. But overall, for this portion of the query, I think things are looking pretty good. So let's sort of move on and see what the rest of it looks like. So in this case, we have this thing called a parallel sequential scan on the business's users table. So our join table is it's going through the entire heap of that table. So we don't actually use any index at all here. It's going through the main table data. The estimate here is that we're going to return a single row. In reality, we return no rows. And we have this thing here that says loops equals 3. That means that there were 3 processes that actually ran through this data. So the Postgres actually started two additional processes in order to go through this data. So that's 2 processes, 2 worker threads, plus the main thread that was already started in order to go through this data. It's going to roughly break the heap up into 3 equals chunks, and then each process takes each chunk and then sort of brings the data back that works or that is returned by this. In our case, we removed 1.7 million rows. This isn't entirely true. This 1.7 million is actually multiplied by 3. So this is returning the number of rows per process that is actually going through this. So we actually walked through 5 million rows, over 5 million rows, to discard every single one of them. That doesn't sound super good on performance there. So in our case, I think most people are going to guess here that we are just going to create an index. So in our case, because if it's a join table, we're going to create a simple composite index on the user ID column as well as the business ID column. The user ID column is useful because that's the part of it that we're actually querying by. And the business ID column is useful so that we can continue to use this index outside of filtering. That's going to be made kind of obvious in just a moment. So we create this index, we let it run, and we run explain again, and we get a slightly different output. If you've noticed now, our execution time is down to 0.036 milliseconds. That is down from our average of 829 milliseconds and down from our initial query there, which was, I think it was just shy of 1600 milliseconds. So now we can see that we're doing this thing called an index-only scan. This is what I was talking about when I created that composite index. Because this part of the query needs to have the business ID in order to pass to the next part of the query, we already have that ready for us. We don't need to actually reach into the table's heap in order to find it. If we had to reach into the heap, it would have taken additional time to actually go from a data structure that's in memory, go find it on disk, read it from disk, come back and actually use that data. So in our case, we could continue to use that index for the entire portion of the query that we needed it for. So hopefully unsurprising, but the user's query also had a similar issue. So we're just going to behind the scenes create the index that fixes that query. And we're going to take a look at pgstat statements again. So in our case here, we are down to 63 milliseconds and 55 milliseconds. If we continue to let our system run, we would see these numbers drop significantly again. But because they started so high, it's going to take a little bit of time to actually get them down. But we can see something new here. We've got a new query that is taking 17 seconds to run. So let's maybe take a quick look at what happened here. So we have the query that doesn't match any of our initial 3 queries that we put into the system. But that's kind of what happens when we develop software, isn't it? New business needs come down, new features are created, but we need to actually make sure that our database, our additional services, not just our programming, not just our data structures in our program itself, but the services that we continue to use are optimized for our workload, because we can create the best code that we could ever write, the most optimized, but if our database is going to be dog slow, then we're going to sort of have some issues. So we have this new query plan, and let's maybe break it down a little bit, but just note that this query took, in our case, 2300 milliseconds. That's quite significantly faster than the 1700 milliseconds that we had initially. We probably had something extra in data, in memory, but let's take a quick look let's try to break this down a little bit again. So we have another parallel sequential scan. We're doing 3 loops again, so we have 3 processes total. Postgres is estimating that we're going to return 29 rows. We ended up returning 26, and we are filtering on the first and last names of the users table. We removed approximately 3.3 million records. Again, multiply that by 3. We removed almost 100 million records. We sorted through 100 million records in order to find 26. That is even worse than the other issue that we had. So we're going to maybe create another index here. Can somebody suggest to me an index that might be useful here? I'm just going to call a name if nobody's going to come out here. All right, Chris. You're muted.
Sorry, I'm a little fuzzy on this, but is it possible to index on the result of like concatenating those 2 columns?
You probably could do something like that, but that would require, I think, either additional storage to sort of like do that. But that's something that you could do. Does anybody else have any, or Chris, do you still have anything?
Oh, my other guess was what Amos just said.
Sorry, I must have missed what Amos said. Was it in the chat or?
Oh yeah, in the chat, first name and last name. Perfect,
yeah. The composite index is exactly what you want here. But before we get onto that, I want to show you something that I see happen in there that I see happen quite commonly. People will create indexes on every single column that they actually want to search for. And this will give you a performance benefit, but not necessarily the one that you're looking for. So let's create these two indexes, and we'll take a quick look at a query plan here just to see what happens. So here's our new query plan after creating our indexes. If you look down at the bottom, our execution time is, call it 60 milliseconds. This is a big win down from our 2300 milliseconds, and an even bigger win down from our 17 seconds, I think it was, initial query time. So I think normally at this point, you sort of pat yourself on the back and call it a day, right? But let's maybe dig into what's actually happening here. So we have this new thing called a bitmap scan, bitmap index scan. And for anybody who's unfamiliar with what a bitmap is, it's a data structure that basically holds either 1 or 0, and it sort of maps to something. In our case, it's going to map to either a record in the heap, or it's going to map to one of the pages in the heap. So what's actually happening here is we're running two different index scans. One's going to go on the first, look through the first name index, and again create either like a data structure that has either a 1 or a 0, depending on whether or not a value was found within that page that matches our query. In our case, it's looking at first name, and we're going to do the exact same thing following the last name column. So at the end of it, we're going to do this thing called the bitmap and. So we're going to take those two bitmaps as an input to an and function. And basically, if both bitmaps have a 1 in the same slot, it's going to keep that 1. If either of them have a 0 in that slot, we're going to get that 0 because we don't care about that data. So that's basically what's happening here. So let's take a quick look at a little bit higher in the query plan. We've got this thing called the bitmap heap scan. So we are actually rechecking that whether or not a given record within the page matches the first and last name, because just because we have a page that matches both first and last name doesn't necessarily mean that a record in that page matches both first and last name. So we went through 6,700 blocks, and we actually removed, call it 7,000 records, additional records after having already filtered. Like I think it was Amos that said that we are going to want to create a composite index on both first and last name. In this case, I just made it last name, first name, and it's completely arbitrary up to a point. One thing to note is that when you have these composite indexes, you can you can use just the first part of that index. So I do not need to, if I had a query that only searched by last name, I do not need an additional last name only index. I'm allowed to use the last name, the last name column from this index. I am not allowed to use the first name column from this index. So if I needed to search by just first name, I would need to create a new index for that, or I would need to swap the order that these columns are listed here. So we create that index, and as we can see now, we are creating or doing just an index scan on the last and first name index. This is now at 0.064 milliseconds. This is significantly faster than even the double index that we had, which was at 60 milliseconds. This is even faster than the 2300 milliseconds that we initially had, and again, the 17 seconds that we saw on the initial runtime. What this means is that you don't necessarily need to, if you create proper indexes, you don't necessarily need to create or use like a caching layer as quickly. You don't need to increase the size of your database as quickly. If you create proper indexes for your system, you will be able to go a lot further without needing to do these additional things. I believe I mentioned earlier that there are 2 caveats to sequential scans. Hopefully I said that. If not, there are 2 caveats to sequential scans. The first being, if you have a sufficiently small amount of data in your table, I'm Canadian, so I use the example of the number of provinces and territories we have in Canada. We have 13. If you had 13 records, I don't know where exactly that number is where it starts to switch, but if you only have 13 records in your database, you will always do a sequential scan. It's just a fact of life. It's going to be faster to just read from disk instead of hopping back and forth from memory to disk, and it's just a fact of life. It's going to be faster. Postgres knows what it's doing. It's still performant. The other one is that if you are pulling out a sufficiently large percentage of your data, I don't know exactly again where that number lies, but say 90+% of your data is coming out of the table because of the result set. it's going to do a sequential scan again. There's no point in reading and trying to find everything, like again, 90% of the records that match from your index, and then going over and collecting all of those records. It's just going to be faster to read the heap directly, and then sort of come back with the result set and actually filter through the last 10% or so of records. This might be something like an analytics query that runs maybe daily, maybe weekly, whatever, maybe manages some data, just something. These types of things are perfectly okay as long as they're not happening all the time. If you have a query that is running like this, that it's retrieving a large percentage of your data, and it's happening on a near every single request basis, you are going to have a bad time because it's going to grind your system to a halt, and you are going to have a database that's basically on fire, and you're going to need to stop your system. Unfortunately, this did happen to us somewhat recently at work, but we were able to quickly fix this issue. But anyway, so sequential scans, not necessarily bad depending on how you're using them. But with that in mind, I do have a query that I like to use in order to keep track of sequential scans. This comes from stock Postgres. You don't actually need any additional extensions or anything else installed. So what this query is going to do is it's going to return the schema that the table is under, the actual table name, the number of times you do a sequential scan, the number of records that are read from a sequential scan, not necessarily returned to you in a result set, but actually read from disk, the number of times that you've done an index scan, and then the average number of records returned by an index, or sorry, by a sequential scan. This is sort of a mixed bag of data because I got this, I did this query after I had already introduced those indexes. But as you can see, especially on the users table, we have, oops, I don't know what I'm doing. We had 255 sequential scans, and I don't even know how big this is. This is like 10 billion, almost 11 billion records that have been returned. That's a lot of data to go through for 255 queries. So use something like this to sort of keep track, making sure that you're not doing something super bad. But again, if you have an analytics query that runs every so often, it's not going to hurt your system. Even if it's not analytics, even if it's just a big query that runs every so often, it's not going to hurt your system. You don't need to optimize absolutely every single query because sometimes there's just no point if it's not run super frequently. I believe that's basically all I've got for today. So I just want to give a quick thanks to everyone on the Postgres channel. Some really, really super smart and helpful people over there on IRC. Same thing goes for the Postgres mailing lists. Some incredibly intelligent people over there. A lot of the developers hang out on the mailing lists. And you don't actually need to mail in questions because there's just a lot of stuff coming through. You can mostly just absorb information like I do. And lastly, just a shout out to my amazing wife and kids. Without them, don't know where I'd be, and they support absolutely everything that I do. So lastly, you can find me online in a bunch of different places. If you've got any questions, feel free to ask tonight. But if you sort of can't think of anything tonight and it comes to you another time, feel free to email me at my public inbox. Otherwise, you can find me basically at Onkers everywhere. And yeah, that's all I've got for tonight. So if anybody's got any questions, I'm more than happy to answer them.
Thank you, Justin. That was really fantastic. We appreciate you coming out. I do also want to be clear that Justin was not the understudy for tonight. I had him as like the headliner for next month. We just ended up swapping. So definitely, as you saw tonight. So one question I have is on Postgres counting. Do you have any experience with that?
What do you mean? Do you mean like actual counters, like increment by one kind of counters?
Oh no, I'm saying like counting. If you have a query, you have to count a lot of rows. Is that something you've dealt with?
I try to avoid that stuff just because it's not very performant depending on how you do it. I mean, it's just going to come down to take a look at explain. It's going to tell you what the problem is with your query. Obviously, these were very simple queries that I ran today. You can get complex queries that have pages and pages and pages worth of details. And I do help my company with some queries like that. I've had people give me 50-line queries that end up at like 5 pages worth of query plans, and you just sort of need to sift through them. There are tools that you can use to sort of help you break these down, especially if you are newer to reading them. If I can figure out chat, explain, I'm gonna not type this in correctly. I will get back on the tool that I like to use. It's not a visual tool. There are some visual tools, but this one, it just breaks it down into sort of like each stage of the query and sort of where you might want to look for issues, and it sometimes is able to sort of suggest to you indexes that you may want as well. There are a lot of tools in this space for anybody that wants to look at stuff like that, but I like to try to keep it fairly simple unless I really need something big. But for counting specifically, again, just sort of look at the explain output. You're going to want a good index on whatever it is that you're filtering by. Sometimes you don't get that. Like I have a couple tables at work that are up to 800 million rows or something like that. And just because I need to know it's a little bit more precise, I do a select count on them every so often. Postgres, depending on your needs, Postgres can also give you an estimate of the number of records in a table because it keeps these types of statistics itself. But if you need to say know how many users are in a certain business, you can't really use that type of query in order to do that. But if you need to, if you're okay with an estimate of the number of records in a table, you can look into these things. Does that sort of answer the question?
Yeah, that's exactly it. Thank you.
So before I jump to you, Owen, there is a question in the chat here. Do you have any personal thoughts on UUID values for ID values? I think it completely depends. In Postgres, I choose to use nothing except for ID, like integer ID values. The reason behind it is that it's not a distributed system. There is one source of truth. You don't need to worry about sort of inserting at the same time and getting the same ID value. But when I've been playing with CockroachDB, I generally use UUIDs because then you won't get that clash for the exact same reason. But within Postgres, I just stick with numerical values. And if I really need to, I read some really cool things. I think it was Pinterest or Instagram or something like that. They created some really cool schema in order to generate ID values that are still going to be unique because they take like a timestamp as well as the machine number, like the instance number of the database that's getting inserted to. So it should still be unique across the entire cluster. Owen, I believe you had your hand up first.
Yes. So I think you might have touched on this. I'm not sure if you answered specifically what this question during your talk, but when you have a what's it called, a complex index or compound index?
Composite compound, yeah.
So many C words. All right. Let's say you have like A, B, C columns, right? A, B, C is your composite index. When you're writing your query, do you need to filter? Does it matter the order that you're filtering? Like I need to filter A, then B, then C?
No,
like where?
Postgres will just do the right thing. So the order that you write your query in isn't actually important. The only important parts are like the select comes before from, which comes before group by, which comes, etc. Where you actually like the actual where clause, it doesn't matter sort of how you have that filter or the order that you have that. Postgres will just do the right thing and be magical and awesome.
Got it.
Nick C.
Hey, could you go in a little bit more depth about the bitmaps and why you decided to use a bitmap index in the example that you showed us?
Yeah, that example was strictly to show you what not to do.
Okay.
Just to show you the difference between what I've seen happen in the past, where people create these multiple, like one index per column that they filter by, versus the composite index, which does the right thing. I want to say it was 100 or 1,000 times faster. So it was just more to contrast to show like, this is what you can do. It's still faster, but here's the right thing to do.
Okay.
Chris?
Thank you. So a question I have on the use of PG stat statements is that what is the overhead for logging that information? Like, is that something that we can turn on in production with like some rather obnoxiously large tables and like gnarly queries? Is that something that we might want to run locally or in staging to, just sanity check some things? Like what is the cost we pay for that instrumentation?
I don't know the exact cost, I'm not gonna lie. Most places I've worked at, we've had it enabled in production. Staging is a great place to have it, but locally, probably not that great. The issue with having it locally is this might not be true for every situation, but we generally don't have a whole lot of data in our database when we do things locally. Postgres is super smart. It goes back to what I said about the number of records in a table. If you've got a couple hundred, Postgres is just going to do a sequential scan anyways. You need to actually do these, like explain, analyze things in production on staging, something that actually mimics the amount of data that you actually have running. If you try to do this locally, you're going to see sequential scans all day and you're going to be scratching your head asking why. And again, the reason is because Postgres will just be faster to read 200, 500 records from the table than it will be to go to an index and try to jump back and forth. So it's perfectly safe to use in production is sort of what it gets to. I'm sure there is some overhead. I don't know exactly what that number looks like though. But to sort of quell some fears, maybe Postgres already keeps a whole bunch of statistics in the background. So this is just a little bit extra added on. Any more questions from anybody? Something from the chat? Cool, I think we're good then. Well, again, thank you everybody for having me. I hope you actually intended to come to this talk. But yeah, thank you so much for inviting me. It was great.